Okay, good afternoon, everyone. Welcome to the IME 765 class. Today is April the 1st, 2020. So we're going to continue our introduction on SVM, support vector machine. So let me share my screen and meanwhile turn off my video. Okay, where's my video? Stop my video. Okay, good. So last time we mentioned the SVM here. Let me first make where it is. Last time we mentioned our SVM, and then in the very beginning of this class, let me have a brief review and also show something that last time I may mention something not accurate, something here. So first of all, the SVM, we come from here, right? And from this formula, I think it's from here. And we know that this one is the distance. And because we're talking about the distance rather than a vector, so that I give an absolute value here, okay? So of course, if fxi equal to 0, then it's gonna write on the separating hyperplane, which means it's on the decision boundary. If it is something else, no matter this side or this side, again, we're talking about the distance. So it's gonna be always positive, okay? And the second thing is that the basic idea of a separating hyperplane is what? By the way, SVM is from separating hyperplane. So currently we're just talking about such a technique like separating hyperplane is to find such a separating hyperplane that the distance between the two classes, assuming two classes only, along the normal direction of the separating hyperplane as maximized. Okay, normal direction means this direction is the normal direction. Okay, so to this point, what we can do is that we can formulate in this way, right? This means, let me box here. So this part is what? This part means the minimum distance, okay? The minimum distance from the classes to the decision boundary. What I mean is, for example, here, for example, the minimum distance from here to here. This class, the distance to this separating hyperplane is this one, because the distance, the definition of a distance from a set to a line, a hyperplane, is always the closest one, the closest point. And then we define this one, this distance as the distance from the set to the separating hyperplane. And here's the same, okay? Without the loss of generality, we can always set this hyperplane to be in the middle such that these two distances will be the same. And hence, I can just go back here. Oh, let me go back. And this one means the minimum distance, okay, from the set to the separating hyperplane. And we want to maximize this distance so that we're going to have a max-min problem, okay? So, and here's something to mention, that this is the hinge loss, which is usually used for model problems, kind of like a classification problems with such maximum margin, especially kind of like a maximum mean margin classification problem, especially for SVM. Actually, hinge loss is created from SVM, and later people realize that it can be used for some other techniques. Okay, and then let me erase this. And then after it, so this is the basic model, the very, very original model that strictly follows the idea of the separating hyperplane. However, this one's a bit more difficult to be solved than a regular single level problem, because it's a bilevel. So we, come on. So we use a trick, that is to rescale this part, okay? Because I can always make W equal to alpha W and W0 equal to alpha W0. So that whatever this value should be, I will make it to be 1, right? Okay, something I miss kind of like mentioned the last time was here. I said that the distance from this line to this hyperplane is 1. No, it is wrong. What I mean is the distance is this part is 1. So the distance should be 1 over W norm. Why? Because come here, have a look at here. See this part. Okay, strictly this part should be inside this bracket. What I mean is this. This part should be here. this, let me draw a box here. This part strictly should be inside this bracket. Why? Because 1 over W times this fx I equals to what? Equals to the distance, right? Absolute value, of course. So here because this W norm is not related with I equal to 1 to n, so that I take it out, okay? However, when you're talking about the distance, the real distance from one line to the separating hyperplane, we do need to include it. Please, let me move it easily. We do need to include it. In other words, the distance from the support vector, one support vector to the separating hyperplane should be equal to 1 over W norm. Okay, norm, I mean 2 norm, no, L2 norm. Okay, so that once this is done, have a look at here. So in this original formulation, this part becomes 1. Right? Of course, positive or negative 1, it doesn't matter. And what do we need to do is only this one, right? That's the reason why we can always use this way, make it to be a 1 level problem, to make this problem to be maximum of 1 over W norm, subject to this part is greater than or equal to 1. Why greater than or equal to 1? Because, okay, delete. Because the part here, right on the support vectors, they are what? They are equal to 1 over W norm. If something away from it, so it should be, suppose this side, it should be greater than it, right? For example, this node, if you substitute inside, it must be strictly greater than 1. Why? Simply because the distance from here to here is strictly greater than 1 over W2 norm, which is the distance here. That's why if you substitute, it should be strictly greater than 1. Similar here, because y is negative 1, okay? So that negative times negative is positive. So again, it's going to be strictly greater than 1. So in this way, we can formulate the problem like this. And previously, what we mentioned is I'm going to maximize 1 over W2 norm, right? And it's equivalent to maximize 1 over W norm square. And I reverse it, it's equivalent to minimize W square, W norm square. You know what I mean? Let me write it down, maybe it's more clear. What I mean is this. So to maximize, let's say whatever, and 1 over W. Let me move this one here. Absolute value, where's my absolute value? Oops, not absolute value, norm. Come on. This one equal to what? This one equal to this. And it's equal to this. Mean of W2. Okay, let me directly use this. Okay, W2. The reason here we have a 1 over it, 2 over a half times the norm W2 is because when we make the derivative, they're going to cancel. That's the reason why we have this. Okay, so in this case, we can build the hard margin SVM. The reason it's called hard margin, again, is because no data can be misclassified. Okay, for all data, you must guarantee that if it's this side, then it's greater than or equal to 1. If it's that side, then it's less than or equal to 1. That's it. No one can, be no one can enter into the marginal region, or even kind of like, for example, a blue point is here, misclassified, no way. So that's why it's called a hard margin problem. And then we mentioned the soft margin problem. For example, if the data is in this way, no matter what, you cannot draw such a hyperplane that there's no misclassification, no way. So in this case, we can improve the model by considering a slack variable. We're going to subtract a slack variable in the right-hand side, which makes it to be 1 minus cos I. And for example, here, For all other cases for this kind of nodes, they're all 0. But for these 5 cases, they are greater than 1 or less than 1. The model is here. The model is here. So let's have a look at the constraint. At the constraint first. This constraint tells you what? Tells you something similar, but here for each data, I do have a stack variable that I can make this case to be, something to fix my constraint, the right-hand side of the constraint. So why this case is greater than 1? Simply because it's a misclassification. 1 minus case. If it's greater than 1, then 1 minus case is going to be negative. But negative means what? Negative means it's on the other side. So it's misclassification. If one case is less than 1, that means what? That means 1 minus case is still positive, but it's going to be inside the marginal region, so that it's going to be somewhere here. Okay, so that's the point. And we do need to add to change something in the objective function. The reason is because if we don't have this one, okay, simple, who cares? I just need to make this one to be as small as possible. And then a very ridiculous case is that I can make W's to be, extremely small. For example, I can even W's to be 0. Why? Because everything's 0, right? And then what I'm gonna do is that I'm gonna, for example, make all cases to be 1. So this is forever correct. Why? Because you always have 0 greater than or equal to 0. Done. So the solution will forever be 0, which is meaningless. This case is a slack variable, and we want to what? We want the violations, the sum of the violations, to be as small as possible. So that we're going to add this item. And this item is relatively easy. In some papers, you can also see like case square. That's another thing. Later, if we introduce the lasso and the ridge, you're going to see. One is regularization. The other is kind of a penalty, sorry, both of them are a penalty, but the meanings of them are very different. Here, for convenience, we set the case to be just a linear item. And because case is greater than or equals to 0, so I don't have to add a absolute value here. So I simply just make a c here. And this c is a user-defined parameter. As a parameter to adjust which part is more important. Suppose you have a c very, very large, then the penalty case will dominate this optimization problem. And then you're going to try to make a relatively big W. What I mean is that you're going to make these 2 lines relatively small. Why? Because the distance is 1 over W norm, right? So if W is large, then W norm is large, so 1 over W norm will be small. So these 2 support vectors will be relatively close. And the cost is that the difference between 2 classes will not be that clear. But the good point is that very few these nodes will be violated. In other words, very few these i's will have case I greater than 0. Most case i's will be equal to 0. Just imagine the case. Today Said is not here, but remember Said, his question, he said, so why don't you, for example, let me use another color. For example, use this blue color. No, let me use a pink color. For example, why don't you draw the support vectors like this way, right? So if you draw it like this way, isn't it like many, many points? For example, this will be normal. This will, we're going to we only have this point, which is abnormal, right? Isn't it good? Yes, it's good. The problem is what? The problem is that if they're so close, so what's the difference between class 1 and class 2? They're not going to be so different. The point is that for SVM, or let's say for any classification problem, we want to do what? We want to find a hyperplane such that the 2 classes will be most different. You know what I mean? So in this case, yes, you can eliminate this kind of violations, or let's say reduce the violations. However, you're going to increase the similarity of the 2 classes. That's why it's kind of really, really a trade-off. And similar, suppose your C is a small number, then what's going to happen? Then that means, okay, who cares? In extreme case, for example, suppose C is 0. Then what's going to be your solution? If C is 0, I try to make my W's to be as small as possible, right? Extreme cases, W is, really, 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 very, very small because C is 0, so that I can make my case to be large. For example, case equals to 1. C is 0. You know what I mean? Who cares how I choose my case? If all case is equal to 1, what's going to happen? You're going to have that yi times This one is greater than or equal to 0. And what is this? This one is nothing but your fx, yi times fx, greater than or equal to 0. That's forever success. It's forever satisfied, right? Because that's the definition. I mean, that's my definition. yi times my fx must be greater than or equal to 0. That means what? That means I can take my w to be 1, to be 0. If w is 0, what does that mean? If w is 0, then that means 1 over w, I'm talking about the norm, sorry. 1 over w norm is infinitively large. That means these two lines will be infinitively away. That's very good and very bad. The very good thing is that in this case, the two classes will be very, very different. The very bad things are, first, it is not practical. Second, in this case, you're going to see huge amounts of predictions and also this kind of abnormal points. Okay, so that's the reason why usually we don't take this kind of very extreme cases. And by the way, c equals infinitive, c equals infinitive is what? It is the case, go back. C is infinitive is the case for hard margin SVM. See it? That means no CASI is tolerated. All CASIs must be 0. Okay, hard margin SVM. Okay, any questions here about the soft and hard margin SVM? No? Okay. Today, let's have a more detailed talk about the dual representation. If you have some papers, I would suggest you to take out the papers, try to write something together with me. It should not be the case that you just have a look at this. You know, looking at it, you will not really get too many or too good understanding about it. You do need to do, you know, follow me, and also after the class, do the operations one by one by one. And the most important thing is to think and ask why we can do this, why we cannot do that. That's extremely important. Okay, first of all, you know the dual functions, right? I'm talking about Lagrange dual, okay? So for this problem, it's a constraint problem. It's, of course, convex problem. And then what I'm going to do is that I'm going to write the Lagrange dual to make it unconstrained. That means I'm going to put both of these two constraints here to the objective function. Okay? Still remember, Ara? You still remember how to write the dual functions? Which is simple. So for this kind of inequality constraints, you're going to do what? You're going to add a mu and then make the right-hand side to be 0, right? What I mean is, okay, I'm lazy to write. Let's use the same method that I used the last time. Ask Wikipedia.
Less than or equal 0 or any value?
Sorry, what?
Constraint will be less than or equal 0, not greater than.
Yes, that's the reason why here I have negative. Okay, so here you go. Suppose you're gonna minimize f at 0x and come subject to this. Here is the inequality constraint, and here's the equality constraint. So the dual function is gonna be formalized in this way. Okay, where your lambda is gonna be greater than or equal to 0, and your nu here is whatever, because this is 0, so it doesn't matter. Okay, but your lambda must be greater than or equal to 0. Now let's have a look at here. If we want to do this way, what do we have? We're going to have it here. Let me write it down. So we're going to have to save my time, I'm not going to write something like w0 because here, okay? So that we're going to have 1 over 2 w plus c, right? Okay, so let me write it in this way so that I have yi wt xi plus w0 minus 1 minus ci greater than or equal to 0. And the second thing is, of course, the same. Ci is greater than or equal to 0 for any I, right? Okay, so the dual can be written in which way? So it's rather simple that the Lagrange dual okay. By the way, this w is a vector. W0 is a scalar. Okay, so because to save me some time, I don't want to, you know, go there and bold, you know, as long as you know, because in my slides, I think it's very clear. Okay, so because here I don't have the /bmx, it doesn't work. In text, I use this one. Okay, so first of all, you're gonna copy and paste this one. So let me copy and paste. That's a good point of online teaching. I can copy and paste. Otherwise, in the whiteboard, I have to copy. Really, I mean, please. I just said it's good, and then it gave me something really bad. Let me select it. Good.
Yes.
This equals to this, and what? And have a look at here.
Minus.
This sign is greater than or equals to. Okay, so that I will have this. I will have a summation of I, and I have a mu I here. However, the sign is minus. Okay, why minus? Because this is greater than or equal to. If it's less than or equal to, you're gonna have a plus. You know what I mean? It is equivalent to, for example, you times -1 for both sides, right? And then you times this one times mu. So that I put this -1 here. Okay. And then the last step is what? The last step is this part. This part I make it to be nu. But be careful here. This nu is similar with mu, that it is also greater than or equal to 0. Why? Because both of them, they're constraints. Sorry, they're inequality constraints. They are not equal. Okay. Well, in the Wikipedia here, this nu is the equal sign. Okay. That's a hello, Mabuba, are you here?
Yes.
Okay. Because I don't know why, like suddenly you appear, suddenly you disappear. I mean, is it internet connection problem or like your video problem? Whatever. Then what we have here is that this nu in the Wikipedia, it is equal, so that it's not constrained to anything. It's free. However, in our problem here, it is not free because I have Kasi is greater than or equal to 0. Okay, the nu is corresponding to the Kasi constraints, so that I do. Sorry, not plus. This is gonna be a minus as well. Sum of I, and then nu I, Ci. Okay, this really looks like V. What's the difference? This is the second one's V. Okay, whatever. Okay, so this is my Lagrange, right? Okay, then guys, how to maximize this one? So what is the difference between this one and that one? The difference is that this is what? Unconstrained problem. Unconstrained problems usually are much easier than constrained problems, right? Okay, so how to minimize this one?
First derivative is 0.
Very good. So what you need to do is that let me write it here. To minimize L, apply the stationarity point. Oh, okay, anyway, whatever. Forget about KKT in this step. Simply get this. Okay, let me use nabla. Nabla L equals to 0 with respect to, let's say W0 and let me see, whatever you have. Kasi, right? Because Kasi is also your original variable, right? Okay, this notation may be a bit confusing. What I mean is that with respect to W0 and with respect to Kasi. Okay, that's the point. Again, be careful. This Kasi and the W, both of them are vectors. Okay, they're vectors. They're not scalars. While this W0 is indeed a scalar. Okay. Now what we're gonna have is here. So partial L, partial W equal to what? So that's the reason why we have a half here. Cancel, right? So this is W. And what is this? This is nothing but mu I, summation mu I 1I xt, xi. Wait 1 minute. I just realized I have a typo here. I don't have xi here. Okay, great. It should be xi. Okay, and then plus W0, nothing with W. So here we go. So that here you get simply W equal to summation of this. Then partial L, partial W0 is even easier. Why? Because the only items here. By the way, this 0 is a vector 0. This 0 is scalar 0. Okay, why? Again, because this W is a vector. This W0 is a scalar. Okay, now we have what? Now, excuse me. Now we have the only item with W0 is right here, right? So that we should have 0 equal to negative mu I yi summation equal to 0 because it's 0, so you can cancel this negative so that you have summation of mu I yi equal to 0. Very good. Be careful here, yi, xi's are all known, okay? While your w, w0, kasi, mu, and nu are variables, okay? Where the first three are the variables from the primal problem, and the second two variables are the what? Are the Lagrange dual variables, okay? And the standard Lagrange problem is what? It's actually a maximum mean problem. Sorry, in terms of this, it's a mean maximum problem because the original problem is this, okay? And now what we're gonna have is these are, where's my kasi? I should have a derivative with respect to kasi as well, okay? So if we calculate with respect to kasi, see here, I have a c here, right? And with kasi, and then here I have a nu here. I think I should say with respect to kasi I. Yes, kasi I. Otherwise, if you brutally do for the kasi, then you will have a c times one vector and a nu vector and a mu vector. It's going to be more difficult. So that I simply write the kasi I. And then I have a kasi here. See it? So that I have with respect to kasi I have c minus nu I, and this I have a negative. Wait. Negative, and one more negative. So it's still negative. So that I should have c minus nu I minus mu I equal to 0. And you can just, I think I move the mu I here, so that it means c minus nu I equals to mu I. Okay, so these are simply, then let me see what 8a to 8c. Okay, very good. Which is equivalent to the stationarity constraint of KKT constraints, KKT conditions. Okay, I should say stationary conditions. Sorry. Actually, what's the difference? Okay, make that a bit more beautiful. Okay, very good. Then remember, again, as a review, can you tell me what are the KKT conditions? I mean, in words, not in formulas. There are 4 types of KKT conditions. What are they? Mahbooba, could you please tell me 2? And Arab, tell me the other 2.
Yes, like primal feasibility conditions, dual feasibility conditions.
You just tell me the easiest 2. Okay, so Arab, you finish the 2 difficult one. It's not my fault. Ask Mahbooba because he just mentioned the 2 easiest one. What are the other 2? So he said the primal dual feasibility and the dual feasibility.
Stationarity.
And the most important thing. The second most important thing. The most important thing is the stationarity conditions, which is which is nabla of L equal to 0 with respect to the primal variables. Okay. The last one is what? CS. Okay. Complementary slackness. Remember what is complementary slackness theorem in the dual in the LP? Remember it? No? Anyway, review it. They are exactly the same. That the slack variables times the constraint, primal constraint, corresponding constraint, I should say, then must be 0. In other words, you have only 2 choices. Choice number 1, that is the slack variable equal to 0. And the choice number 2, sorry, not the slack variable, I should say the dual variable equal to 0. Choice number 2 is that the primal constraint itself is a binding constraint. That means the inequality becomes equality. Okay, so the second group, what I wrote here is the primal feasibility. That your this is nothing but this constraint. 6b must be satisfied, and this is the CS. These 2 are the CS. Okay, 8F and 8E and 8F are the CS. Okay, so that I have KKT conditions 8A to 8C. 8D is the primal feasibility condition, and 8E and 8F are the complementary slack conditions. And finally, 8G, is a definition of the variables plus. Be careful. this C greater than or equal to 0 is the primal feasibility, okay? This is from the primal feasibility. And 8G as a primal feasibility for C. And dual feasibility for mu I. Okay, so I want to make sure that this 8 is correct, is clear, okay? Which are actually KKT conditions. Okay, now we're gonna substitute 8A to 8C into 7, okay? So you're gonna do some operations. Actually, this is super simple. Why? Because this makes what? This makes all these items to be, let me see. This 8E, look at 8E, makes this big item to be 0. See it? And then you have what? Mu I C I equal to 0. So this item is also gone. See it? In other words, both of them are over. Both of them are done. And you just substitute this one here. This is super simple, right? Because what is the norm of this one? This is nothing but this times this t, right? And then it's gonna be just the inner product of that itself, and then plus C times Ci, so that you immediately have this. Okay, I'm not gonna do the details. You do it by yourself after the class. So immediately have this. See it? Very simple. This nu I is from here, from this one. C minus mu I equals nu I. Okay, so you have let me see. Where wait, where did I get this summation of mu I? Let me see. This part is really very simple. It's immediately from here. But where do I should have here C times Ci, right? And C times Ci equal to what? I forgot where I got this item. Summation of them equal to the summation of nu I. Where I get this summation of nu I? CRBR, this is 0, this is gone. This is also gone. So I only have this item. But let me. Ci. There should be a method that can immediately eliminate this Ci. C minus. Okay, I get a point. It's actually from here. So for this item, I didn't directly make it to be 0. Although yes, you can somewhat make it to be 0 because of this. What I did is here, I combined this part with that part. I combine this one with that one. So it becomes what? It becomes C minus nu I times Ci. See it? For each item, right? So once I have this one, have a look at this formula. C minus nu I times Ci. C minus nu I equal to what? Mu I. In other words, I have mu I Ci, right? And but give me 1 second. But why here so if that's the case, I should have a nu I. I should have a Ci as well. Let me think about it. Why don't I have the Ci here? Anyway, I'll recalculate it after the class and see. Probably there's no mistake because finally, I mean, all the calculations are around this. I will do it after the class. Let's keep the lecture. So you put all this and we get this. Suppose this is correct. So we get actually a big improvement. What is that? Because here I have only one variable, which is mu. But look at here, I have 4 variables. And the very good thing is that mu is the dual variable, which is greater than or equal to 0, right? So what we just need to do is that we just need to solve this problem with respect to this. The reason you have mu I 1I equal to 0 is because of this. It's from 8b. You do have mu I y equal to 0. And of course, your mu I is greater than or equal to 0. So where did you get mu I is less than or equal to c? It is from here, from 8c actually. Why? Because I know that my nu I is greater than or equal to 0, right? And now I have mu I plus nu I equal to c. That means what? That means my mu I must be less than or equal to c. Okay, so that the whole problem 8 plus this variable, this Lagrange dual function is equivalent to this simple problem. This problem is really, really simple. Get a point here? And some people call this problem as the Wolf dual. Well, for me, I would keep, kind of like the dual representation, whatever name you want to call it. Okay, so excuse me. So the very clear thing is what? We can actually have two tricks to get the W star and the W0 star. Why? Because suppose I solve this, by the way, Mahbouba, how to solve this problem? In your research topic that you did in February, you should already have learned a method to solve this problem, which is super simple. Hint, gradient method plus something. No, this is not gradient method. That method is still ADMM. But here you can ignore the ADMM because this problem is really too simple. The only thing is my mu is what? My mu's are decision variables. Okay, x, y, all of them are known. Okay, so anyway,
it's a linear problem.
This is not linear. This is quadratic. This is quadratic, not linear.
Yes, quadratic. Yeah.
Okay, so anyway, think about it. But this problem, suppose I have already had the oracle. This problem is any solver, you can get it. Extremely simple. Or you can use a central path method. For example, the very first idea is you can, in the beginning, set the mu equal to c, and gradually reduce the mu. Why? Because mu equal to c is the maximum case, and gradually reduce the mu because I'm gonna maximize it. Okay, and find the direction, improving direction. Okay, now let's have a look at, suppose I already have the mu's, how can I get the w's? Why? Because finally your prediction is based on w, right? W are your primal variables. Mu is just a dual variable. You don't have to, for example, I substitute this mu, okay, I substitute this one, and then I solve the w and the w0 and the c. No, you don't have to do it. What do you need to do? Oh, by the way, one very important question. Why is the maximum? Rob, this is specifically for you. Why it's maximum? Have a look at here. My problem is the minimum problem. But why here I write a maximum of this? Because that is the depth. Because of what? Mahbouba, can you answer why it's a maximum?
Because this is the dual problem, and
very good.
We're optimizing with respect to dual variables.
So that we get what? The optimality gap, right?
Yes.
Abdullah, not Abdullah, sorry, Arab, you got the idea? The standard Lagrange dual problem is, I don't know whether it's here. Okay, so here, max min, strictly I should say max inferior, okay, inferior problem rather than max min. So that the inner level is the primal problem where the dual variables are fixed, which is the, what is this? So small. This is, let me make it bigger. Okay, where it is, which is the u here. And outer level, it's a maximal problem, which is, suppose for each nu I have a solution here. So which u will maximize this part? Okay. So go back to our problem here. Look, what is mu? Mu is a dual variable, right? So corresponding to the dual level, it should be a maximal problem. Okay. So strictly, you should do what? You should do, suppose I have the mu here already. Okay, you substitute it back, and then you have the mu, so you should have the nu, right? Because mu plus nu equal to c, right? So you have the nu. Now you have the mu and the nu, both variables, so these two become constants, right? And then you're gonna minimize this with respect to w, w0, and the c, right? Okay, the truth is that you don't have to do it. You don't have to resolve the problem again. You can buy some linear combinations, immediately get a solution. How do I get it? Okay, let's do this. First of all, this problem is like this way. Okay, I've already known this, and I want to. This is actually not accurate. What I need to do. Sorry, there's a typo here. What I need to put is actually I should put the mu and the nu here and make this one to be minimum problem. Sorry, here's a typo. I will correct all these typos here. And what we can do is first we can take advantage of the KKT first stationarity condition, which is 8a here. From there, what we see is 8a is here. W star means the optimality, the optimal solution of this one must be mu star y xi, right? That is something for sure. And now have a look. Suppose I have this, and then we can take advantage of some other conditions where it is here. The complementary slackness. That's also the reason why just now I called this is the second most important thing. This tells you what? This tells you either mu I is 0 or the second part is 0, right? Okay, what does that mean if the second part is 0?
Binding constraint.
Yeah, of course, it's a binding constraint. That means my what? This part equal to 1 minus Ci, right? Okay, so and then we have what? My W equals to this part, mu I star times this. However, a lot of mu I is gonna be 0. Why? As long as this one is not equal to 0, then your mu I is, sorry, as long as this one is not equal to 0, then your mu I is 0, right? But the mu I 0 is meaningless here. So I want to count where the mu i's are not 0. That means I can count the part here. See it? One of them must be 0, so that I can just count the part in S. This means my mu i's are greater than 0 rather than equal to 0. Then I can what? Then I can just do this. Of course, you might say, hey, what if this is 0 and the mu I itself is also 0? It doesn't matter. You just count one more thing. It doesn't matter. You know what I mean? What this tells you is that if S is not satisfied, then mu I must be 0. You know what I mean? So that's the item. Okay, so I can calculate the W simply by this way, and done. That's it. Super easy, right? Y, X, again, are constants. Okay, they are known data, training data. So I know how to calculate my W star. The second thing, before it, I need to mention one more thing. That is, this tells you what? This tells you that W star itself is determined only by the set of S here. Support vectors. They supported the decision of W, okay? Actually, W is much more important than W star, right? W star is just a shift, but the W tells you the direction of your separating hyperplane, right? Okay, now have a look. How to get the W0? Ideas? Actually, it's right here. How to get your W0? So by this, what do we have? We're gonna see what? We're gonna see, okay, since your C equals to nu I plus nu I plus mu I, what I need to see is that whether my mu I equal to C or not. That tells me that if my mu I equal to C, my nu I must be 0, right? Okay, so what's the point? If your nu I must be 0, okay, the point is here. I know that my nu I times Ci is 0. In other words, if my nu I is not 0, in other words, if my mu is less than C, strictly less than C, this tells me what? This tells me that my Ci must be 0, right? Okay, then go back. Where? Okay, here we go. My Ci, if my Ci equal to 0, then have a look at here. This is greater than or equal to 1. This tells you what? Have a look here. So a trick that I'm going to define similar as here. I'm going to define the G set to be the index set where mu I is strictly less than 0 than C. Okay, and this is equivalent to say that my Ci must be 0, right? Again, it's because what? Because nu I plus mu I equal to C. Mu I less than C, that means nu I is greater than 0. Then by the second complementary slackness problem condition, if nu I is greater than 0, that means my Ci must be equal to 0, right? In other words, in this case, for I is in the intersect of S and G, meaning that for this I, such that your mu I is strictly less than C and strictly greater than C, then you're going to have what? You're going to have that 1I fxi fx equal to 1, right? And this equal to what? This equal to this. Okay, this representation is just, you know, just from here. I substitute this part. I substitute this to this. So to this actually. I substitute this to this W, so that I have this part, right? Okay, now have a look at here. I know mu I know y, I know x, I know j, and this is 1. So immediately I solve the W. See it? And your W equal to what? W immediately equal to this divided by this one minus this one. And because yi is either positive 1 or negative 1, so 1 over y is equal to yi. So I have this. See it? Okay. So this is very simple. In other words, I can In other words, I can evaluate this W0 star from any number, any data point, as long as it's in this set, of course. However, to make it stable in numerical calculations, what do we want to do is that we want to get the average. That means I'm going to sum both sides for all I is in the set of S intersection of G. Okay, and this means the cardinality, means how many i's are in S and G, intersection of G. And then the right-hand side is again summation for I is in S and G. I get the average of the W0 star. Get a point? So in this case, you don't have to solve the you don't have to resolve the optimization of minimize this one. You only need to do this kind of linear algebra tricks. Everything's linear. Which one is easier, solving an optimization problem or simply calculate, even not solve, calculate linear, this kind of linear matrix? Of course, this one is much easier, right? Okay, so in this way, we successfully solve the problem. Get a point? Okay, so this is, some people call it as a way of computing the SVM, and my personal preference is to call it as the dual representations, because this is, I mean, this is just nothing. You're playing the tricks of the dual problems and KKT. That's it. Okay, get a point? Any questions here? No? Okay. In the following, let's introduce a little bit about kernel trick, or I like to call it the kernel technique. And I know, Mahbooba, you are very interested in the kernel. First of all, let me ask you, both of you, have you used the kernel technique or kernel trick before? No? Arab, in your general, I remember you have had a class, which is, what's the name? General linear, GLM, right? GLR, general linear regression. Is it? What is the name that you learned from Department of Statistics? A course started with general. I forgot. General linear regression or something.
No, I did not take this type of course.
You didn't? Okay. I will be surprised if they didn't introduce the kernel trick, because kernel trick is widely used in regression. But here, I'm talking about the kernel trick for the SVM. Actually, basically, they're exactly the same, no difference. Maybe there you're going to use more about the Gaussian process as you use the, the Gaussian kernel more. But here, I mean, this again in general. So what is the idea of the kernel trick? The idea is this. For example, consider the data in this way, and ask you make a prediction. And you're gonna say, okay, let me make a soft margin. For example, I made, for convenience, I just draw the support vectors, okay? The separating hyperplane is right in the middle. For example, I can draw in this way, okay. Why so ugly? No, I'm gonna can I control Z it? Okay, yes. For example, I'm gonna, do something like this. Well, do something like this. Look at this red data. Still a lot of violations. You see it? And actually, whatever you do, as long as you use the linear, it doesn't matter. See the point? So immediately, is it possible that I can let me make it a bit bigger? I can make it something, for example, like this way. For example, like something like this. Will that be possible? Right? Okay. To answer this question, first of all, we need to see how do we really interpret this kind of data. First of all, what we can do is go back to that soft margin representation, dual representation. Here I use soft margin, the main reason because as long, for the hard margin case, SVM case, I just simply consider C equal to positive infinity, okay? So it's a special case of the soft margin, so it doesn't matter. And by the way, what if I want to do the dual representation here for the hard margin? How to do it? Be careful here. In this case, you will have mu plus u is nothing. Be careful here, okay? In other words, something you took advantage here need to be redefined, okay? It's gonna be homework. Do it by yourself. I'm not gonna introduce it here. It's really very simple. You just do step by step as what I did here. You're gonna get the answer. Okay. So focus on the soft margins VM that we just mentioned, and you have this representation. And have a look here. Let me ask you this. Suppose I give you the mu, I give you the x, y, everything. I give you even, as we mentioned from here, these two equations from 11 and I didn't mark it. Let's say 12, or let's say this equation. I can also calculate the mu star, W star and the W0 star, right? In other words, I have already had everything. Great. So I can do my classification. Then if you do the classification, what's going to happen? What I mean is that if you do the classification, what is your decision boundary? You're going to say, okay, easy. My decision boundary is fx, which equal to W star tx plus W0, and you substitute everything there, blah, blah, blah. You're going to have this, right? Actually, I forgot to substitute the W star here. W star can be further, substituted by this way, okay? And I think it's going to be better for me because this is going to show the kernel idea even more clear because here you have another kernel. Anyway, okay, so x equal to this. Everything looks purely simple. The problem is what? The problem is that this is going to give you a very clear, what? Linear function. Get a point here? It's going to give you a very clear linear function. Why? Simply because it's in this form. So what if we want to, kind of like fix it? Is it possible that I can make it a nonlinear? For example, here is inner product of xxi, and here in the W star item, you should have another item which is x star xj inner product of xj and xj itself, right? So what if we change this inner product of x and xi, or sometimes you have xi, it doesn't matter, to be a function of x. For example, hx and hxi. And by the way, by using this one, what I mean is the inner product, okay? You know what is inner product, right? I don't need to introduce it, okay? So, and because we use inner products, sometimes we mention about Hilbert space. What is Hilbert space?
Hilbert space. Inner product space.
From your glasses, yes, I can see your screen. I know you are searching.
No, I'm not.
Okay, so what is Hilbert space?
It's an inner product space with infinite dimension.
Partially. Hilbert space is something the same as Euclidean space. The difference is that the metric is not going to be Euclidean space. It's not going to be L2 norm. It's going to be the inner product. That is the Hilbert space, okay? And actually, if we want to make it deeper, I wish probably I don't have time, to be honest. If I have some time, I'm going to mention a little bit about the kernel trick in linear regressions. And you're going to see the choice of this h is not random. This h must make this vector to be positive definite. No, I should say this. In some cases, it only needs to be positive semi-definite. But in many cases, we want it to be really positive definite. It's gonna, have a lot of very good points, good properties. But here, I'm not gonna tell you, let's say, how to generate the h or something. And to be honest, in many cases, h will be one of them, especially number 1 and number 2. Number 3, for Arab, you may have seen it. What is this function? Sigmoid function. Did you use neural network before? So in the neural network, one thing, very important thing is what? Sigmoid function, right? Okay, and have you seen this one? Widely using sigmoid function, especially in some cases, something like, for example, 1 over 1 plus e to the power of x, or negative x, or some linear expression of the x. Very standard, candidates for being selected as sigmoid functions, right? Okay. So, but here I just let you know that this is the idea. Again, this is the introduction. Otherwise, I can spend more than 1 lectures to introduce what is the kernel. It's just a very basic level here. So in this case, we just want to change the xxi to be hxi, where h as a nonlinear function. Okay. Now the thing is, if I just simply literally change them, okay, here's hi x and here's hxi and hxi prime, and you just make everything to be h. So you have this item form, right? And from this form, actually, h exists only in the form of such an inner product, right? In other words, who cares what your h is? What I really care, I'm talking about in terms of to solve this problem, okay? I only need to know what is the inner product of hx and hx prime, right? It doesn't have to be hx prime. For example, we call it hxi and hxj. I could be equal to j, okay? It could be itself, inner product of itself, for example, the norm itself. Okay, so I define the kernel function of x prime to be the inner product of hxi and hxi prime. Again, xi prime could be equal to xi. And I don't care what really the h itself is. I just care what my k, the kernel function, is. Okay, this is the kernel trick. Okay, as I mentioned, at least many choices of the kernel's functions are this. First is the polynomial. I'm gonna choose it in this way. This is a degree polynomial function. Very simple, okay? The second way is from Gaussian process, or let's say the Gaussian kernel, and it's also called radial basis function, RBF. And I guess you have seen RBF, this notation, along many times. Maybe you don't know RBF is the same as Gaussian. So for me, I'll always use Gaussian because my memory is not good. I cannot really remember this name. Okay, so but Gaussian, everybody remembers. Look at this. What is this? Exactly the Gaussian distribution. See it? Get a point? Okay, so that's how you see the Gaussian kernel everywhere. It's from here. Okay, and clearly, if we have a look at the degree d here, that means what? A high degree polynomial function means what? You're gonna have a higher curvature, right, in the decision boundary. Similar, a large gamma here is gonna give you what? Make the curvature high, high, and hence you're gonna create something like islands. And we're gonna see the examples after it. You're gonna see, really, we're gonna have this kind of islands, okay? The neural network, here, I didn't use anything about neural network, but indeed, the neural network models things, many sigmoid functions are defined in this way, okay, as their kernel. Okay, now let's have a look. Suppose I have already determined my k kernel function. How to make the decision? You're gonna make the decision in this way, the same, right? Now you understand why by doing in this way, it's gonna your decision boundary could be a big curve, could be very curved. Why? because I put the k x xi here. This x is what? This x is the target data or the test data. This xi is the training data. Okay, so in this case, because this k can be, for example, suppose it's a Gaussian kernel, of course your decision boundary will be very, very curved. See it? So why?
I have a
Yes.
question at this
Yes.
point. So why the kernel function f of x is less than 0?
Why less than 0? Because
Yes, for class 1.
Equal to 0 is the boundary. So we're going to classify it by two cases, less than 0 or greater than 0. Remember? So for example, in the SVM, how do we classify? This is your boundary, right? Let me ask you, suppose I have a point here. What is your class? Your class is class 2,
Greater
right?
than 0. Yep.
Why class 2? How do you know it's class 2? In terms of algebraic, rather than the graphic way. How would you do it? Simple. You're going to substitute this node to your fx, right? And you're going to see whether fx is greater than 0 or less than 0. If it's exactly equal to 0, that means it's exactly on the boundary. You can either choose 1 or 2, it doesn't matter. But if it's strictly greater than 0, then it's class 2. It's here. Of course, you can name it as class 1. It doesn't matter. What I mean is it's corresponding to the class that is represented by y equal to 1, positive 1. Okay. If the point is here, then it's corresponding to the class described by y equal to -1. That's it. See it? Remember, I mentioned it here. Where it is, I forgot, but I'm 100% sure. Something here. And I mentioned it 3 times. Here you go. For target data x, we're going to classify it to class 1 if this one less than 0, and the class 2 if it's greater than 0. That's it. Okay. So the same here using the kernel function. Where my kernel function? Using my kernel function, I'm going to do this. Less than 0, I'm going to do class 1. Greater than 0, class 2. Okay. And then question is, have a look here. Where? Here. Again, why this is a plan? Because of what? With respect to x. Okay. Again, these xi's are known number. They're just a number. You can consider it as 1, 2, 3, 4, 5. Okay. So it's not quadratic. You only have an x here. And this w star, the formulation is similar. You also have a kernel. And I'm going to fix it after this class. I'm going to substitute it back. Your w star is this. See? Again, everything's known. And the only thing is x, j, x. This is actually a constant. W0 is immediately a constant. You even don't need a kernel here. It's just simply a constant. See it? So in this case, everything's going to be extremely easier. Okay? And I'm going to have what? I'm going to have the kernel boundary, which is a curve, rather than a simple hyperplane. Got a point? Okay, now let's have a look at an example. This example is based on the data here. This data. Remember, this is, simply we just use the SVM soft margin, and that's really bad, really bad. Let's have a look how it's going to be if we use the kernel technique. So here we use the Gaussian kernel, RBF. And for the Gaussian kernel, I do have a parameter, which is gamma, right? And here I change the different gammas, and also I change the C. C is a parameter here to adjust which one, a balanced parameter to determine which one is more important in the soft margin SVM. Okay, so I have, let me make it a bigger. Okay, so this is a case where my C's are 1, and my C's are 1, and my, move it here. And my gammas are from gamma equal to very small, and then gamma is bigger and bigger. So very clear, when gamma equal to 0, it's going to be the same as the linear. Why? Because if you have a look at the Gaussian kernel, gamma equal to 0, that means it's 1. It's really meaningless. It's going to be a constant 1, right? Okay. Now if I have a gamma, no matter it is small enough, at least I have something because it's exponential so that the impact is huge. Then what I have is if I increase the gamma, you see what? It's going to be less and less smooth. This is smooth, less smooth, less smooth, very, very, I don't know, insmooth or unsmooth, one of them. And you're going to see, oh, looks they're very good, something. Yes, of course, because there's no bias. Remember in the lecture, I remember on that day, only Arab was in my class about the what? The trade-off of bias and the variance. Okay. Actually, the trade-off of bias and variance is a common thing, not only in the KNN. Okay. Where I remember we put we got the formulation, we worked together. And remember you asked me a question, and in the beginning I could not answer it in the class, and after the class I wrote some more things and I can answer it, you know, and interpret an easy descriptive way to interpret it. Remember it? Okay, and here we also have the same problem, that a trade-off between the smoothness, or let's say the variance versus the bias. Way it's in this way, it's very smooth. Smooth means the variance is small. It's not like from here, just a little different, and then your class is going to be very different. You have a big variance. Here, my smooth is relatively small. However, by the definition of bias, your expectation of the parameter minus its true value, this could be large. Why? Because, for example, suppose here, you expect, suppose here, your expectation of this one would be what? Would be blue. However, your true value is red, the class. So your variance, so your bias could be large. Something similar here. So not similar, something opposite here. Your bias is gonna be small because you make it extremely tight, kind of have this kind of islands. So of course, looks that, you know, everything works very, very well, looks oh so accurate. However, you greatly increase the variance. It makes your prediction not that reliable. Reliable in terms of the variance, not in terms of, you know, the training data. And in this case, you're going to easily have what? Overfitting. See the point? Overfitting, why? Because you can create a kind of too perfect model that works specifically and only for the training data. You know what I mean? And later we're going to discuss the cross-validation. And you can see, if you use these kind of ways from the training data, you say, oh, great, it's so beautiful, everything's nice, accurate. Yeah, great. And then you do the test data, you're going to cry. Everything's so bad. Overfitting. That's a problem, okay? So trade-off. And there's no, in general, there's no rule to say, hey, which one should I really test it? Which one should I really choose parameters? I don't know. Depends on, you know, different data. And then the real truth is that we're gonna tune the parameters for a long time sometimes. That's, I mean, the data science, okay? And then let's have a look. So any questions about this? And this.
So at this point, you are suggesting gamma should be a hyperparameter, like
high parameter or hyperparameter, you said? High parameter?
Yes.
What do you mean? You mean
that
you
means
want gamma
we have to make some trial and error to get a proper gamma, or is there any method to? Yes.
Yes, the truth is that you're gonna do it via cross-validation. You're gonna choose a gamma and to see whether it's in your threshold, and then you're gonna use it to do the testing data. Remember it? Remember lecture 1? We have 3 groups of data. For validation,
yes.
For training, for validation, and for testing, right? And then you're gonna go through the validation stage and the testing stage. And if really, suppose in this case, it's for the training data, it looks perfect, right? Okay, try the validation, the testing data. If all of them are so good, okay, you're done. But probably not. Probably you're gonna fail in the test stage. And you're gonna suffer the problem of overfitting. You know what I mean? So probably you may prefer something like this and like this. You know why? Let me give you a super simple example. Oops. Come on, come here. Okay. Suppose, okay, so the original data is here, from here. Data from here, right? Okay. Now, Booman, let me ask you, what if I have a point? Let me choose a Okay, no, I cannot give you a red point. Otherwise, that's biased. What if I have a point here? Which class do you think it is? Class
Negative
red,
one.
right? The red
Yeah.
one, right?
Yes.
If I have something here, you're gonna predict it as the green one, blue one, right?
Yes.
Okay, very good. Let's keep these 2 points, and let's go here. Come on. Unfortunately, I cannot fit these 2 points in one graph. Clear. Let me draw. What we just drew was something like this and this, right? It looks beautiful, yes. No problem, right? Okay, move this point here. You see what happened?
Yes.
Overfitting. Why? Because this works too good on the training data. It's too tight, such that, I mean, by our eyes, it's very clear this point should be a red point. But if you do it this way, great, it's a blue point, and you're wrong. See the point? That's the reason why. Don't think that, oh, the higher accuracy, 100%, that's great. No, not necessary. You could have a problem of overfitting and make your work completely meaningless. You know what I mean? And go to lecture 1. I remember I showed you a 0-1 loss, an example, and use the what? Directly define the data at the point itself. Then you're gonna always, no matter what is the data, you're gonna 100% have a 100% accuracy. Are you happy about it? No, because you're wasting your time. It's meaningless. Overfitting, 100% overfitting. You know what I mean? So that's the case, okay? It's not guaranteed that gamma is great, is always good. I mean, it's not guaranteed that in case of this kind of things, it's always good. You have to do it via cross-validation. And then you're gonna see whether it's really good or not, okay? Any other questions? Because in the next thing, I'm gonna mention the change of C. Here, as I keep C to be 1, and I change the gamma, which is the parameter for the Gaussian kernel. Okay. Okay, now let's go to this case. So here, I keep gamma to be 001. The reason I keep gamma to be 001, I want to make it relatively smooth. If I make this one and I change C, it's going to be really a disaster. I wanted it smooth. Okay. Now you can see this is again the same. C equal to 1. And in this case, C equal to 10. Okay. And in this case, C equal to 10,000. 1,000, and in this case, C equal to 10,000. Again, recall, what does C mean? C means the parameter or the weight to balance the 2 items, the marginal distance and the violation. Remember it? The bigger C it is, you're gonna have a higher penalty, a stronger penalty for the violation, right? And that's the reason why here, for C equal to 10,000, it looks really, really good. Look, there's no violations at all. See it? While in C equal to 1, there are a lot of violations. You know, by violation, what I mean is either it's in the marginal region, or it is a misclassification, especially misclassification. Okay, so here you go. But to be honest, for this specific data, looks that this works the best. Don't you think so? Because if I ask you to, do classification, probably I'm gonna do a classification something like this way. That's just my personal opinion. Different people may have some different opinions. I don't know. For example, what if there's some data here? For example, there exists some data in this way. Some data, oops, come on. Why only red? Can I make a colorful heart? Okay, delete it. Let me use this. No, I should be a black color. Yes. Suppose what if something here? How would you predict? It's difficult. To be honest, I don't know, because why, for example, from this graph you're gonna predict it to be red, but why red? Because it's something here, right? I can also predict it to be a blue. From my view, both are correct or both are wrong. I don't know which is the correct answer. So this conclusion works only for this specific problem, okay? So that for this specific problem, I would prefer something like this way, rather than like the way that we just mentioned in the previous class, in the previous example, which is here. I don't like this. This could be something very, very bad, and also this and this. For example, this means suppose I have a data here. Suppose I have a data here. It's going to be green. Sorry, it's going to be blue. And why? Clearly, if you ask me, I'm going to say this one's going to be red. But here, everything looks very good for me. Again, it's a very personal idea, and it's a very problem-specific conclusion. Okay, any questions?
So we are changing
the things.
Penalty function, penalty value like C
Yes.
as a penalty. C
Yes.
is a penalty in our objective function, and
yes.
Can we use both? Like,
of course. You can, of course,
function
change the gamma and meanwhile change the C. Of course, you can do it.
Okay.
And the real thing is, yes, we're doing it, really. We're doing it, and also by cross-validation, usually. And also, you can use something like, no, ARC, BRC don't work here, because here, the number of parameters are fixed. Some cases, for example, suppose people want to have a CI rather than a common C. In some problems, then in that case, you may use AIC or BIC. Arab, have you learned AIC, BIC before? Hello, Arab? You are muted, yes. Have you learned AIC, BIC before?
No, most probably.
No?
What's the full form of AIC?
Sorry, AIC, BIC. There are some criteria to select models. Have a balance about the number of parameters versus the accuracy. And you're going to get the perfect AIC parameter. And if I have time, I'm going to do it right in the class. It's too important to show it. It's really, it's simple, but extremely important. And then you're going to see why the 2 and where is the coefficient 2 from. It is from derivative, actually, but it's really beautiful. And anyway, if we have time, we're going to discuss it. So any questions about today's class, which is first a basic introduction to the kernel trick, and also the dual representation. No question? Okay. So in the next class, we're gonna introduce the. This is something that I mentioned in the last class that I just added on Monday, or yes, I think on Monday, because I wrote it here. I said in this lecture we will mainly discuss the 2-class classification problems. Although at that time I said in the last section I will introduce a little about the multi-class problems. And then I had to look at it here. What? I didn't have the last section, so I immediately added the last section. I forgot it after finishing the kernel trick here. So in the next class, we're gonna mention this one, and then let's see. Would you prefer some examples of SVM? But in this case, it requires, like for me, I mainly use the MATLAB. For Python, I'm gonna use it, let's say in the class of next semester. It may not be that. I'm not pretty sure. I would prefer, let's say, we introduce some simple examples, maybe, and then we're going to go to the next lecture, which is linear regression. Linear regression, we're going to have 2 lectures because they're really important. The first lecture introducing something basic about the basic forms and the mathematics about linear regressions, and the second thing is going to introduce something about like, no, I haven't. I think I may put this one in the first lecture as well. Yes, and then we're gonna introduce some algorithms about it. Okay. There any questions? No. It's the time to be finished because it's already 4:20. Okay. Very good. Thank you very much for today's lecture, and see you in the next class. Bye bye.
Yeah. Thank you. Have a good day. Bye.
Thank you. Bye.